Everyone, we're going to talk today about lots of different things, so symmetric games and lots of things about mixed strategy, Nash equilibria. But let's start with symmetric games. Okay. Okay. So a two-player game is symmetric if and only if two conditions hold. So first one is that both players must have the same action sets or A1 equals A2. And the second condition is that U1 of U1 of x comma y should equal U2 of y comma x. Okay. For all x and y in A1 in the action set. What the second condition means is that if you flip the actions, then you get the utility of the other player. So let me explain what that means in a second with an example. But these are the only two conditions you need. Okay? So do you remember the prisoner's dilemma game where we have cooperate, cooperate, defect, defect, P1, P2? We had a 3, 3, 5, 0, 0, 5, 1, 1. So this game is symmetric. The first condition that both players have to have the same action sets, that's satisfied because A1 is the set C comma D, which is also the same as the set A2. The second condition is satisfied because, as you can see, let me change the color. U1 of something like C comma D must equal U2 of D comma C. So if you flip the actions and the name of the player, you should get the same number. U1 of C comma D is 0, U2 of D comma C also 0. And so that is satisfied, right? U1 of D comma D, when there is nothing to flip, equals U2 of D comma D, right? And that holds true for all of these. Another way to visually see this is to imagine a negative 45-degree line going through your payoff matrix and seeing everything reflected on the other side. So see, this 3 is reflected by this 3. This 5 is reflected by this 5. The 0 by the 0, this 1 by this 1. Does that make sense? You can't answer me because this is a video. Hopefully that makes sense. If it doesn't make sense, again, we can talk about it when we meet next, which is, wait, I'm waiting for you to answer. It is September 9th. All right. So that's what a symmetric game is. What's a symmetric Nash equilibrium? A star, well, let's suppose A star is a Nash equilibrium. A star is a symmetric Nash equilibrium if and only if A1 equal to A2 and A A1 star equals A2 star. All right, so for A star, the action profile to be a symmetric Nash equilibrium, well, first, it has to be a Nash equilibrium. But then it also has to satisfy two additional conditions, which is that the action sets have to be the same. So capital A1 has to equal capital A2. And the second is that the action chosen in equilibrium has to be the same. So if you go back to the prisoner's dilemma game and map out the best responses are Nash equilibrium, which is D comma D, is a symmetric Nash equilibrium. So here DD is a symmetric Nash equilibrium. Now the game doesn't have to be symmetric in order for the Nash equilibrium to be symmetric. For instance, I believe we saw this game in our first lecture. It's called Barkov-Stravinsky. I think we had a up, top, bottom, left, right back then. But let's say we do 2, 1, 0, 0, 0, 0, 1, 2, player 1, player 2. Here, the equilibrium SS and the equilibrium BB, they are both symmetric Nash equilibria, even though the game itself is not symmetric. This game is, so here you have A1 equal to A2, and you have A1 star equal to A2 star in both our Nash equilibria, which are BP and SS. And so both of these are symmetric Nash equilibria. But because U1 of B comma B is not equal to U2 of B comma B, and the same also holds for 2 is not equal to 1, and U1 of S comma S is not equal to U2 of S comma S. This game is not symmetric. These two equilibria are symmetric Nash equilibria. Okay. What else? You can have the same game have both symmetric and asymmetric Nash equilibria. That's also fine. And we'll talk about examples of that in the lecture later today. But for now, I'm going to pause. This is going to be video number 1, and it's all about symmetric games and symmetric Nash equilibria.